This video presents Maxwell's mechanical formula for the heat capacity ratio. The heat capacity ratio, gamma, is defined as the heat capacity at constant pressure, Cp, divided by the heat capacity at constant volume, Cv. The heat capacity at constant pressure, Cp, is defined as the amount of heat input, delta Q, required for a unit increase in temperature, delta T, while maintaining constant pressure. The heat input, delta Q, is equal to the sum of the increase in internal kinetic energy and the work done, P delta V. The total internal kinetic energy includes both translational kinetic energy, ET, and rotational kinetic energy, ER. The heat capacity at constant volume, Cv, is defined as the amount of heat input, delta Q, required for a unit increase in temperature, delta T, while maintaining a constant volume. Because the volume remains constant, the work done, P delta V, is zero. Consequently, all the heat input contributes to the increase in internal kinetic energy, which encompasses both translational kinetic energy, ET, and rotational kinetic energy, ER. The formula for the heat capacity ratio, gamma, can be obtained by substituting Cp and Cv into the definition of gamma. Then, replace delta Q with delta ET plus ER. Note that P delta V is converted to delta ET using the relationship PV equals 2/3 ET. Taking the derivative of both sides gives delta PV equals P delta V plus delta P V. Since Cp is defined under constant pressure, P delta P equals 0. Consequently, P delta V equals 2/3 delta ET. Substituting this equation into the expression for gamma allows us to express gamma in terms of translational kinetic energy ET and rotational kinetic energy ER. We can simplify the formula for the heat capacity ratio, gamma, by defining a new variable, alpha, as the ratio of total kinetic energy, ET plus ER, to translational kinetic energy, ET. Based on this definition, ET plus ER equals alpha ER. Replace ET plus ER with alpha ER. Cancelling out delta, ET, allows us to express the heat capacity ratio, gamma, with the single variable alpha as 3 alpha plus 2, divided by 3 alpha. So, we have just derived Maxwell's mechanical formula for the heat capacity ratio, gamma, as gamma equals 3 alpha plus 2, divided by 3 alpha, where alpha is defined as the total kinetic energy, ET plus ER, divided by the translational kinetic energy, ET. Maxwell presented this formula in On the Dynamical Theory of Gases, published in 1867. For monatomic gases, which consist of single atoms, the rotational kinetic energy, ER, is negligible compared to the translational kinetic energy, ET. Therefore, the ratio of ER to ET is 0. Because ER is negligible, alpha equals 1. Since alpha equals 1, the heat capacity ratio, gamma, equals 5/3. For diatomic gases, which consist of two atoms, the ratio of rotational kinetic energy, ER, to translational kinetic energy, ET, is approximately 2/3. Substituting this ratio into the formula for alpha, gives alpha, equals 5/3. Substituting alpha into the formula for gamma gives the heat capacity ratio, gamma, equals 7/5. For polyatomic gases, which consist of more than two atoms, the ratio of rotational kinetic energy, ER, to translational kinetic energy, ET, falls within a range between 2/3 and infinity. By substituting this ratio into the formula for alpha, we find that alpha ranges between 5/3 and infinity. Substituting this value of alpha into the formula for gamma gives the heat capacity ratio, gamma, in a range between 7/5 and 1. In summary, Maxwell's mechanical formula for the heat capacity ratio, gamma, is 3 alpha plus 2, divided by 3 alpha, where alpha is defined as the total kinetic energy, ET plus ER, divided by the translational kinetic energy, ET. This formula connects the heat capacity ratio to the mechanical properties of particles and agrees with the empirical data. Comparing Maxwell's formula to the formula based on the equipartition theorem shows that F is equal to 3 alpha. Since alpha is the ratio of total kinetic energy divided by the translational kinetic energy and is not always an integer, 3 alpha is not always an integer. This explains the puzzling question of why F, which is equal to 3 alpha and is defined as the degree of freedom in the equipartition theorem, is not always an integer in the empirical data. Thank you for watching.